Okay. Hi. Hello. Welcome back. So I am 𝐒𝐲𝐫𝐭, a senior CPU design verification, currently working at Synopsys. So I have been working in Synopsys for more than 1 year now. And prior to this, I have been working as a CPU design verification engineer at Intel for 2 years, for 2+ years, basically 2 years, 4 months. And prior to that, I have done my MTech from IIT Kanpur, and I was a topper there. So, okay. I am very passionate about the VLSI industry, the Verilog system, Verilog, the digital, okay, and digital design, okay, and verification. So in this playlist, in this video, we are trying to cover the walkthrough, basically HDLBits walkthrough. So basically, I'll be solving and showing you how to solve the HDLBits problems. And before we start, uh, I would like to again tell you that, okay, please try to solve these problems by yourself. And if you cannot solve these problems, or if you want to know my approach, how I can solve it in a different way or in a better way, uh, then check this walkthrough. Before this, try to solve it yourselves. And after that, feel free to watch it, learn from it. And if you have a different approach, please let me know. And if you have any doubts, if you are not able to understand my way of solving the problem, uh, drop the doubts in the comment section. Okay, I'll try to clear your doubts. And if the doubt is like, if I can solve it in the comment section, I'll do that. Otherwise, I'll create a separate video to solve that doubt. Okay, and the community members will also be there to help you. Okay, so feel free to drop any comment in the comment section. And yeah, please do like, share, and subscribe this channel. Like this video, share it with your friends, this playlist and this video. And yeah, mm, if you can support this channel in any way, that would be great. Okay, so let's start. I'll share my screen. So in the last video, we covered till this 3-bit population count. Now we will see what is there in this problem and then try to solve it. Okay. So you're given a 4-bit input vector. So it's like input is a 4-bit vector. We want to know some relationships between each bit and its neighbor. So each bit and its neighbor. So what is the relation between them? We want to know out both. So in out both, what we will have is each bit of this output vector, each bit of this output vector should indicate whether both the corresponding input bit and the neighbor to the left, okay, higher index, are 1. If both, so it's like we have 4 bits in the input. So out both, so 0, the 0th bit of out both will say 0 and 1. These two bits are 1 or not. Should indicate whether both the corresponding input bit and its neighbor to the left, which is the higher index, are 1. For example, out both 2 should indicate if in2 and in3 are both 1. Since in3 has no neighbor to the left, the answer is obvious. We don't need to know out both 3. Okay. So what we will do is we will say assign out both. Okay. There are many ways we can do it. We can use a for loop as well. Okay, but let me see what they are asking for. Each bit of this output vector should indicate whether any of the corresponding input bit and its neighbor to the right are 1. For example, out 2 should indicate if int 2 or int 1 are 1. Each bit should indicate whether any of the corresponding input bit and its neighbor to the right, input bit or neighbor to the right, any of the bits are 1. For example, out 2 should indicate whether out in 2 or in 1 are 1. Since in 0 has no neighbor to the right, the answer is obvious. We don't need to know out any of 0. Each bit of this output vector should indicate whether the corresponding input bit is different from its neighbor to the left. Each bit of this out vector should indicate, okay, whether the corresponding input bit is different from its neighbor to the left. For example, out different 2 should indicate if out in of 2 is different from in of 3. Out different 2 should indicate if in of 2 is different from in of 3. For this part, treat the vector as wrapping around. So in 3 is neighbor to the left is in of 0. So what we can do here is we can separate things out. We can write in uh, out both. We can write in one aside. We can concatenate and do and things like that. Otherwise, we can write a for loop and for 3 1 2 3 or 0 1 2, and here we can write out different uh, 0 1 2, and the rest one we can write separately. Okay. Each bit of this input vector should indicate whether the corresponding input bit is different from its neighbor to the left. Whether the corresponding input bit is different from its neighbor to the left. So the neighbor to the left is different or not? I mean, is that bit or and the left bit different or not? For this example, output should indicate if in2 and is different from in3. And for this part, treat the vector as wrapping around. So in 3's neighbor to the left is in of 0. Okay. So what we will try here is we can also use assign statements inside always blocks. Always at the rate star. We don't need always actually. We can write an initial block. Initial. Now what we will do is we will write a for loop for I equal to 0, int I equal to 0, because we will write a continuous statement, so we don't need to repeat that always. I less than 3, I equal to I plus 1. Okay, I should have written begin here. And now we will write an end. Okay, and in the middle, what we will write is out both of, and we will assign here So what we will assign here? Out both of. So it's like out both of 2 should indicate if in2 and in3 are both 1. So out both of I equal to in of I and in of I plus 1. Out both of I equal to in of I and so in of I plus 1. Okay. Out both. Okay. Assign out in I out any of I plus 1 actually. Okay. So why it is I plus 1 is out any starts from 1 to 3, not 0 to 2. Okay. We are going from 0 to 2. So I plus 1 equal to, for both what we are doing is we are saying both of 2 means in of 2 and in of 3. It's like in of 2 and in of 3. For out any, we are saying out any 2 if in 2 and in 1. So it's like out any of 2 should indicate if in 2 or in of 1. Into in I plus 1. Okay. Out any of 2 should indicate if in 2 or in 1. Okay. Or in or I can say in I or in of I plus 1. Okay. It's the same thing we are doing or. So and assign out different. Should actually do I plus 1 and I. It doesn't make any difference, much of a difference, but it actually looks good because that is how it is given. Out any of 2 is in of 2 or in of 1. So it's like we are trying 2 equal to 2 or 1, 1 equal to 1 or 0, and 3 equal to 3 or 2. That way. Okay. Out different of I. So we will do 0, 1, 2 in the loop and 3 outside the loop. Okay. So indifferent of I equal to, what we will do is out different of 2 should indicate in of 2 is different from in of 3. Out different of 2, which is out different of 0, let's say. So it's different from its neighbor to the left. So 0 means in 0, in 1. So in of 0, in of I XOR with in of 1. Okay. Not 1, basically I plus 1. For out different 0, we are saying in of 0 and in of 1. Out different 1, it's 1 or 2. Out different 2 means in 2 or 3. Out different 3 is not there. So we need to write this. Okay. We can say assign out different of 3 is equal to in of 3 or in of 0. Why? Because they said consider there's a wrap around. For this part, treat the vector as wrapping around. So in of 3 is neighbor to the left is in of 0. So in of 3's neighbor is in of 0. Out different 3 is in of 3 XOR in of 0. Okay. So that will be the solution. So let's submit. Okay, procedural continuous assignment to register is not supported. Register. Okay, so they are treating this as a register. Now what I can do here is I can just say 𝐿 of I. 𝐿 of I. You can create generate block. After 𝐿 of I, we have a semicolon. We have generate. We have end generate. Okay, let me check. 𝐿 block in Verilog. Example. Okay. So what we need to write is 𝐿 of I. Then we have to generate, and then we have to write end generate. And here we should not write int. Okay. We should not write int because I is now not an integer anymore. We write generate and end generate, and we write 𝐿 of I. Okay. So now that is done. Let's submit. Okay. And let's see how their the name. Okay. 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 So this requires a name. So it's like line number 10. We know loop. Okay. Loop for just some any random name. Okay. I don't know why this is needed till now, but this works. So see status success. So this is how you write a 𝐿 code to replicate these 3 parts of the code again and again. Okay. I don't want to say out both of 0, output of 1, out both of 2, out both of 3 like that multiple times. So it's better to use 𝐿. Okay. Because here it's like out both of 0, 1, 2. What if this input is a 100-bit vector? We will not write 100 times, right? So it's like 3 into 3 is 9 times we have to write, assign this, assign that. So it's better to write a 𝐿 block in this case. Okay. And in cases where this value will be more than 3, 4, 5, 6, 10, 20. Okay. Okay. 𝐿 we have covered previously in one more problem. You can go back and see. Okay. So yeah, let's move on to the next problem. Previously, we have solved 𝐿 in this problem, I guess. This generate for loop for 100-bit BCD adder. Okay. So now let's move on to the next problem. Okay. I hope this logic is clear. We can also split it. We can just say out both of 0, out both of 1, the way I did it here for 1. Okay. Because it was not becoming part of this 𝐿. So we put it out. Okay. It was not matching kind of thing. So it's not in 3 XOR in of 4, where we are writing in of I and XOR in of I plus 1. It was a wraparound condition. So we wrote it separately. Okay. And this loop runs for 3 times. This is the 4th iteration. This should be the 4th iteration. Also, it won't fit here with I and I plus 1. Okay. It will be I and I plus 1 mod of 4. It's like I plus 1 mod of 4, which becomes 0. If I do I plus 1, it becomes 4. Mod of 4 is 0. So that way we could have written, but in the loop, but not needed. Okay. So writing it separately here is the easiest option. Okay. Okay. So let's move on to the next problem. Let me see what is there. It says even longer vectors. Okay. Get SV 100. So out both out any out different. The same thing we need to do. Uh, it's like a 100-bit vector. Previously, if anyone would have done in the shortcut way, they have to anyway replicate 𝐿 here. Okay. So you are given a 100-bit vector, same relationship, some relationship. So it's like, you know, out both 98 should indicate in 98 and in 99 both are 1. Both are 1. So, and here it's like out any of 2 would indicate if either in of 2 or in of 1 are 1 to the right. Okay. And out different means here there's a wrap around. Same thing. Okay. Let's solve this directly. It's just the exact same way we solved the previous problem. Okay. So without wasting time, assign out different of, so what we are doing is to the left. So out, okay, so in 99's neighbor, okay, out different of 99 equal to in of 99 XOR. This is what we were talking about. Okay. Out different 98 should indicate in 98 XOR in 99. Here it like in 99 XOR in of 0. After that, gen where of I generate and generate. Okay. For I equal to 0, I less than 99. So I need to run from 0 to 98 basically, or 1 to 99. It's like 98 times 0 to 98 plus 1, 99. 99 I have written here. Here I will run from 0 to 98. I equal to I plus 1. In Verilog we don't have, here we will write loop for, it's like for loop basically, and we will write begin end. Okay. And then we say assign. Here we will write I plus 1. Why we are writing here I plus 1, I will tell you. Out both of I. So here in both, what we are doing is out both 98 should indicate in 98 and in 99. 98 is 98, 99. Okay. In I and in I plus 1 plus 1 equal to in I plus 1 or in I. So what we are doing here is out any to the right. So we need to say out any of 2, out any of 2 is equal to either in 2 or in 1. So in 2 or in 1. Okay, that is how we are doing it. Out different is never to the left. So 98 should indicate 98 and 99. So out different of I is equal to in of I XOR in of I plus 1. It's like to the left. Okay. So yeah, let's submit. Yeah, the status is a success. Actually, it seems big or difficult. After we have solved the last one, it's the exact same thing. It's not very difficult after all. Okay. I hope the screen is properly visible. If not, we will increase the font a bit. Okay. So yeah, we got a success. We hope it is visible. Okay, let me increase the font anyway. Okay. You should be able to watch it properly. Otherwise, what's the point? Okay. So okay, that's the solution for this problem. So let's move on to the next one. So after this basic gates, we have multiplexers, 2 to 1 multiplexer, 2 to 1 bus multiplexer, 9 to 1 multiplexer, 256 to 1 multiplexer, 256 to 1 4-bit multiplexer. Okay. So let's create a 1-bit wide 2 to 1 multiplexer. When select equal to 0, choose A. When select equal to 1, choose B. It's very simple. What we do here is, we have also discussed this, assign out equal to select. If select is 1, it says when select equal to 0, choose A. So when select equal to 1, choose B. So when select equal to 1, choose B. Otherwise, choose A. Okay. If select equal to 1, choose B. That is what it says. Otherwise, choose A. Okay. So this is the simple way to solve it. Okay. So yeah, it's a success. Very easy problems. You can see the waveforms also. For every problem, you will see waveforms. You can check if something goes wrong. You can check where it went wrong, why it might have went wrong, what is my input, what is my output. Okay. So what is the logic you have written? You should be able to explain it to yourself. If you can't, probably there is some mistake. Okay. If you need any kind of discussion, feel free to ping me in the comments. I will also share my uh, email ID, so you can you know write uh, if you need any kind of help or support. Okay. So okay, great. So let's move on to the next problem. Okay, I'll also, if possible, give you uh, a link to book calls in case you want to talk to me or discuss something uh, eh, related to Verilog or system Verilog with me. Okay. So yeah, let's move on to the next problem. You might have already seen the way I solve problems and the things I know already. So okay, many people say a lot of things, but while solving problems, they get stuck. Okay, we can understand how they can think and how they can solve problems based on how they approach problems. Okay, so yeah, let's move on to the next one. We have a lot of problems pending, so it's like, arithmetic circuits, and then we have Carnot maps. Okay, we have sequential logic, we have latches, so many problems. We have counters, we have shift registers, we have more circuits, and finite state machines. Oh my god, it's a never ending list. And we are building larger circuits, and we have verification things, finding bugs. Okay, and we have verification writing test benches and CS4. I don't know, they're probably adding something. Great. Why not? Uh, yeah, great. So let's see what they're asking. Create a 100-bit wide 2 to 1 multiplexer. When select equal to 0, choose A. When select equal. Okay. It's actually the same problem. So what we need to do is assign out equal to select. If select is 1, choose B. Otherwise choose A. Okay. If select is 1, choose B, otherwise choose A. That is what we did. But now what is different is out is a 100-bit vector, B is a 100-bit vector, A is a 100-bit vector, select is a 1-bit vector. Okay. So I am checking if select is 100-bit output gets the 100-bit value of B. Otherwise, 100-bit output gets the 100-bit value of A. Okay. So that's the difference. So yeah, let's submit. If semicolons are fine, yeah, fine. So we should get success. Great, as usual. Let's. So the way I solve problem is impromptu. I don't practice before because I don't want to invest much more time on it. You know, then teaching here becomes boring. I am doing the same thing again and again. Okay. I try to use my time very efficiently. So I'll probably solve Python, or I'll probably, study uh, computer architecture or UVM or some different thing. Okay. Uh, Rather than practicing these problems just so that I can solve it correctly. So you might have seen I make mistakes also sometimes because I didn't solve them before. This is the first time I'm reading it. I am solving it on the go. Okay. Mux 9 to 1 B. Okay. Create a 16-bit wide. So A, B, C, D, all these are like 16-bit wide inputs. The wide A, B, C, D, E, F, G, H, I. So we have 9 inputs, 16-bit wide. Okay. Each of the inputs is 16 bits, 9 to 1 multiplexer. Okay. If select equal to 0, choose A, select equal to 1, choose B, etc. So select equal to 2, choose C, else choose D, E, F, G, H, I. For the unused cases 9 to 15, set all the output bits to 1. Set all the output bits to 1. Okay. Okay. It is also easy. It depends how you want to solve it. So I want to solve it in conditional operators. Using conditional operators, I'll say assign out equal to select. So I'm checking what is the value of select. So how I am checking is select equal to 1. So what happens is if I do select, it checks true or false. So now what I'm doing is I am saying select equal to, if select equal to 0. So select is a 4-bit value. So I'll say 4 tick D0. So it's like decimal 0. Or what I can say is hex of 0. If it's hex of 0, or I can say decimal of 0. Okay. What I will do is I'll say do something. Okay. Output equal to A. I'll say output equal to A. Otherwise, okay, there's a way I can, write multiple lines. If select equal to, okay, we'll write it this way. 40 D1 B. Otherwise, 40 D0 A. Otherwise, 40 D1 B. Otherwise, check 40 D2 C. Otherwise, A, B, C, D, E, F, G, H, I. Else this something. Okay. So it's like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C. Okay, 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. And in case of 9 to 15, else we don't need to do anything. D, E, F, G, H, I. So we have A to I. Based on the select, we are checking if it is 0, 1, 2, 3, 4, 5, 6, 7, 8. Then if it is 0A, if it is 1B, 2C, 3D, 4E, 5F, 6 means G, 7 means H. So output gets H. If it is 8, it gets I. Otherwise, if it is not 8, like 0 to 8, then it gets 16 tick. So what is output is a 16-bit value and it should get all ones. 16 tick H X F F F F. Okay, its F is 1111. So or I can write B 1111 1111. Okay, so this is just to explain. But if I want to reduce this, as a 16 tick H F F F F. Okay, so these are 4 Fs. It says it's a hexadecimal representation. Okay, so very easy. Okay. Oh, okay, let's submit. Okay, 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 okay. That's what I thought. It should work. It's still not working. Okay, okay. And not do it this way. What I will do is so this is what I'll do. Say I made it a one-liner thing. Okay. Now it should work. Okay. It should work. Okay. Now let's submit and see what happens. Now it should work. So let me see the solution. Okay. How they have solved it. Case select. Okay. This is also a good way to solve it. A very good approach actually. Case select. So what we are doing here is we are saying case select. So you can also watch the solutions that are given. So what we will do is we will check what is the value of select. If it is 0, out equal to A, otherwise out equal to B, otherwise out equal to C. It's a very great way to solve these kind of problems. Okay. What happens here is you don't Like you don't unnecessarily create big logic. So you can just say case select, check the value of select. If it is 0, do this, do that. Okay. Before that, what they do is out equal to tick 1. Okay. So tick 1 is a special literal syntax for a number with all bits set to 1. Or there are multiple ways. You can say 16 times 1 tick B1. So you can replicate it 16 times. Or this is a very good way to write it 16 tick HFFF. Okay. There are multiple ways to solve this problem. This case statement is a very good thing. What they're doing is out, they are setting it to all ones. And when select matches any of this, the out value changes to the appropriate value. Otherwise, out remains as all ones. Okay. So this is the logic. That's why they are presetting it to 1. If select doesn't match any of the outputs, the output select doesn't match any of these values, the output remains at 1, all ones. Okay. The special literal syntax you need to remember. Tick 1 means all ones. So it's like 1 1 1 1 1 1 1 1. So it's like 16 ones. Depends on how many number of bits are there in the output. The out is a 16-bit vector, so it will get 16 ones. Okay, great. It's a great solution. I really appreciate this. Okay. So now let's move on to the next problem. Okay. So now they are saying create a 1-bit wide 256 to 1 multiplexer. Okay. The 256 bits are all packed into a single 256-bit vector. Select equal to 0 should select in 0. Select equal to 1, select bits in 1. Select 2, selects bits in of 2. So now what we need to do here is okay, uh, create a 1-bit wide 256 to 1 multiplexer. Okay, so it's like 256 down to 1 multiplexer. So it's like 256 inputs, 1 output multiplexer. And these inputs are all packed into a 256-bit input vector. Select equal to 0 should select input of 0. If select equal to 0, output should be equal to input. And select equal to 1 means we should select input of 1. And that way we should proceed. Okay, sorry. I was something else was running on my mind. Okay, 1 bit wide. Okay, got it. How to solve it? Now output is 1 bit. It should get uh, select will be a value input of that. Okay, input of select. Yeah, that makes sense. See, if select value is 0, if select value is 0, I should get input of 0. But I need to do this uh, in a for loop. That makes sense. Uh, we have to write if this is that. Otherwise, directly we can write in of select. Let me see what happens. It should also work actually. It's a good way. Oh, great. So if select equal to 0, select value will range from 0 to 255. Input values are also ranging from 0 to 255. So input of 0. So when select equal to 0, output equal to input of 0. When select equal to 10, output equal to input of 10. When select equal to 250, output equal to input of 250. It's a great way to solve it. Let's see the solution, how they have solved it. I think, yeah, they have also solved it the same way as us. Great. Okay. Create a 4-bit wide 2 to 1 multiplexer. So out is now a 4-bit value. In is this. So how we need to write is, we need to write assign out equal to in of output is a 4-bit value. Okay. What we can do is we can concatenate. Okay, we can concatenate. How we will write is out should get, if select equal to 0, we should get 0, 1, 2, 3. Okay. Okay. Select into 4, 4. So we need to somehow multiply by 4. Okay. And then so 0 into 4 plus 3. Okay. And then we can do the same thing here. Okay. So what we can do is plus 2 plus 1 select into 4. So we are concatenating them. Yeah. Great. Status success. Okay. So let's see the solution. Yeah, they are also solving in the same way. Yes. I mean, the brackets are not needed. Uh, I thought of not giving the brackets, but then I thought let's specify them to make it more easy to understand. What happens is, in because of the BODMAS rule, So multiplication has a higher precedence. So we do select into 4 first, and then we add plus 3 or plus 2, whatever it is. Okay. So yeah, so it's the same thing, nothing much different. Okay. So it's a success anyways. You might have understood how to do it. Okay. Now let's move on to the next problem. Okay. Okay, we have covered multiplexers. Great. Now we are coming to arithmetic circuits. Okay. So what we will do here is we will see what this is asking for. It says module, top module, input A, B, output, C out sum. What it is asking, create a half adder. Okay, half adder. Sum equal to A XOR B. So if you know the half adder thing, you can check. If you have any doubts, please feel free to ask. So assign carry equal to A and B. Okay, it is very easy thing, so I am not explaining explicitly. Sum you must be knowing equal to A XOR B, carry equal to A and B. Sorry, not carry, it's C out. Sum and carry out. Okay, so let's submit because it's a half adder. Okay. Mhm. Okay, so create a full adder. Full adder adds 3 bits and produces a sum and carry out. So what we will do here is we will say sum equal to A XOR B XOR C in. Oh, okay. We need to write assign statements here, and we need to assign C out equal to A XOR B and C in. It's like whenever A is 1 and C in is 1, or B is 1 and C in is 1. So it's like A or B is 1, A or B, any of them is 1. Either A or B is 1 and C in is 1. In that case, we will have uh, like carry out becomes 1. Otherwise, if A and B, so if A and B both are 1, then also carry out is 1. Okay. So you can just put this in brackets. You can also put this in brackets so that you know for sure this calculates first and then this calculates and then this calculates. Then this calculation happens. Okay. Here it's not needed anyways. So you do anything first, it's the same. XOR. Okay. So yeah, it's a success as usual because it's a very simple one, very simple problem. Okay. So let's move on to the next one. Now that you know how to build a full adder, make 3 instances of it to create a 3-bit binary ripple carry adder. We need to make now 3 instances of it to create a 3-bit binary ripple carry adder. The adder adds 2 3-bit numbers and a carry in to produce a 3-bit sum and carry out. The adder adds 2 3-bit numbers. Okay. And a carry in to produce a 3-bit sum and carry out. To encourage you to actually instantiate full adders, Okay, instantiate full adders. Also output the carry out from the last adder and is carry out usually C. For 2 bits we can write manually. We can write, but we don't have a full adder here. I don't want to create a full adder again. So what I will do is I'll say uh, I'll write, we can use genvar of I generate end generate for I equal to 0, I less than 3. So it's like 0, 1, 2. Okay. I equal to 1, 2 I less than 3. Why? Because we have a scene which we need to give. I equal to 0, we need to do it separately. Otherwise, rest of the things we can do in the loop. I equal to I plus 1. I am getting a feeling that we will get the same thing with 100 or something. 100-bit binary adder. I think this will be the same thing, just that we have to do it for 100. Okay, let's try this out after this. I'll just copy the same code and paste it there. I don't want to write the same thing again. Okay, so I equal to 1, I less than 3, I equal to I plus 1. And then what we will do is we will say loop for, and then we will say end, and then we will write sum of I. So it's like sum of 1 equal to A of 1 XOR B of 1 XOR C out of 1. Okay. So the first, sorry, I minus 1. Okay. So what happens is the first adder on the right hand side, it takes A of 0, B of 0, C in, and results in C out of 0. So input is A of 0, B of 0, output is C out of 0. For the second one, we have input as A of 1, B of 1, C in of C out of 0. A of 1, B of 1, and C out of 0. Okay. So if I want to write it, what happens here is, okay, what happens here is we have a ripple carry adder. Okay, we have a ripple carry adder. We have the first adder and full adder 1, or full adder 0, let's say. We have here C in. Okay, and here we have A of 0 and B of 0. Okay, and then we have C out of 0. Okay, and then we give that to the next one. Okay, we give that to the next one, and here we take A of 1 and B of 1. Okay. And C out of 0 as input, give C out of 1 as output, and sum of 1 as output. Okay. So I hope now you can understand. For full adder 1, we will give A of 1, B of 1, and C out of 0 as input. Okay. So C out of I minus 1. Okay. Now we will say C out of I, which is C out of 1, equal to, what we will say is A of I XOR B of I, and C out of I minus 1 okay, uh, yeah, okay, and then what we do is this, or, so if A or B is 1 and C is 1, or A and B are 1. Okay, so I'll just copy this and we'll change it to AND. Okay, so this is the thing, and we'll write assign statements here because we want to replicate the whole thing with assign, and we will say assign, no, we'll just copy these two. Okay, no problem. We just copy these two and say okay, sum of 0 is equal to A of 0, B of 0, not C out, it will be C in now. Okay, and similarly here also we will say C in. Okay, and we will say here is 0, C out of 0 equal to A of 0 XOR B of 0 and C in, or A of 0 and B of 0. Okay, so now after we have C of 0, we use C of 0 here. Okay, great. Let's copy this entire code because we will need this and submit. So it will be a success because yeah, great. We have a status success. Okay, so we have adder 3, so 3-bit binary adder. Let's move on to, we have a success, so you can see the logic. Okay, things will be clear to you. I hope it's visible. Okay, we have already increased the font uh, to 175%. It should be pretty much visible now. Okay, now let's move on to the 100-bit binary adder. So this is now solved. This is now solved. What it says, create a 100-bit binary adder and a carry in to produce 100-bit sum and output. Okay, so this is different. This is not the same thing. Okay, here we can use a shortcut. Okay, because carry output doesn't require the intermediate outputs. What we can do here is, so this strategy you can only apply when Cout is 1 bit. This you can only apply when Cout is 1 bit, and let's say sum is like 100 bits plus carry out is 1 bit. A is 100 bits, B is 100 bits, carry in is 1 bit. Okay. You don't need the intermediate carry outputs. So you don't need to do the actual ripple carry addition. What you can do here is you can say assign, okay, and then what you can say is carry out, so which is 1 bit, and then sum, which is 100 bits, so total 101 bits, equal to, okay, A plus B plus C in. So what happens here is you do arithmetic addition of 100 bit number with another 100 bit number plus another 1 bit number, which results in a 100 or max 101 bit number, which I can assign it here. So it's like sum is 100 bit, and then the one more bit which is to the leftmost, yeah, the MSB bit, it goes to the carry out. So if there's any carry, it will go to the carry out. Okay, this is a very shortcut way to solve this kind of a problem. Okay, so it'll be a success. See, it's a very good, very nice problem. Okay, let me see if I have a similar problem here. Okay, so this is also a similar problem I can see, but it says use this BCD full adder. This BCD adder. Okay, okay, we will come to this later. Let's go to this and see what they are asking. Implement the following circuit. This is what we implemented actually, but they are saying there's no carry in. Okay, there's no carry in, and I don't need the intermediate carries. Okay, so what we can actually do is we can either implement this way, we can either implement this way, and say wire. Okay, what we will do here is we will create intermediate carries 1 2 3 4. Okay, 1 2 3 4. So carry 4 down to 0. So 1 2 3, so it's like 3 down to 0 wire. Okay, 3 down to 0, 3 down to 0, C out. Okay, this is an intermediate wire I am creating to make my problem easy. Okay, and then we have the usual gen var. Okay, now Cin is not there. What we will do is we will say XOR with 0, XOR with 0, or we will say 1 tick B0. Okay, 1 tick B0. In case of Cin, we just said 1 tick B0 because we don't have a Cin, so we treat it as 0. Now we have this, and C out is an intermediate wire. We created sum and C out. For A and B, we need X and Y. We need to replace all A with X. Okay. We need to replace all B with Y. Okay. And then what we need to do here is C out, all things are okay. This C out of 3, C out of 0, 1, 2, and 3. This C out of 3 equal to sum of 4. that is also we need to say assign sum of 4 equal to C out of 3. This is what we need to mention here. Okay. Now if we do that, okay, so it's like 1, 1, 2, 3. So not less than 3, it's less than 4 now. Okay. 0, 1, 2, 3. Okay. Now what we will do is we will just submit. Okay. Because we have sum of 4 equal to carry out of 3. Sum of 0 we know, carry out of 0 we know. Okay. So let's submit. Great. You can see success. Okay. You can see this solution, how I have done it. Okay. I think it's clearly visible. Okay. And what I will do here is, I will change this logic. I will change this logic and say sum assign sum. It's like sum equal to sum along with the carry. It's like a 4-bit sum equal to A plus B. If I just do A plus B, we will get a 5-bit value because A is 4-bit, B is 4-bit. Max we can get 5-bit. We assign that to sum. Simple. If I just submit, you know, it's solving right now. I mean, it's trying to run it. Object, sorry. We need to give X and Y. I forgot. Status success. Okay. So this way also we can solve it. I don't know why they give sometimes A, B, sometimes X, Y. It's the same thing only. Anyways, easy problem. Let's move on to the next one. The module, top module, ABS overflow. What we need to do here is assume that you have two 8-bit, two complement numbers. 7 onto 0 and B 7 onto this number added to put to this 7 onto also compute whether a overflow has occurred. Okay. Assume that you have. So I'll just cover these two problems and then we will stop today. K-map we'll do in the next video. So we have two 8-bit 2's complement numbers. Two 8-bit 2's complement numbers. So A is a 8 2's complement number, B is a 2's complement number. These numbers are added with a signed overflow has occurred. Okay, signed overflow is a concept I can explain, but I don't want to explain now. It's a relatively tricky concept. We have to give you 4 examples to show you in what cases overflow occurs and in what cases overflow does not occur. Okay. So overflow occurs only when I'm just giving you a preliminary, when the output expected is positive but the output looks negative. Okay, in that case we call that an overflow. Okay, if the output should be positive, so if I add two positive numbers and if I get a negative number, or if I add two negative numbers and I get a positive number, only in that case overflow is uh, it is called as overflow. Okay, so if I add two positive numbers, so it's like if I add two numbers starting with zeros, and if I get the output as starting with zero, there is a positive number, so then there's no overflow. If I add two negative numbers, so two numbers starting with one, and if I get a result which is starting with one, then the answer is a negative number, so there's no overflow. But if I add two positive numbers, so starting with zeros, okay, and if I get a number which is starting with one, that becomes a overflow. Okay, and if I add two negative numbers starting with one, and if I get a result which is starting with zero, then there's an overflow. Okay, and what happens if I add one positive and one negative number? So if one of the numbers a and b is positive, that is it starts with a zero, and the other number is negative, that is it starts with a one, then there cannot be any overflow because there will be subtraction. Okay, so let me do that anyways. So we are adding it. We will say sum equal to a plus b, and overflow say assign. So when a is positive, a is positive and b is positive and result is negative, so a of 7, a of 7 is positive and b of 7 is positive and s of 7 is negative. So how we represent negative is we give a bar. Okay, then we get overflow, and in what case we get overflow is if a is negative. So if a is negative and b is negative and s is positive, basically the seventh bits, the msbs of a, b is positive and s is negative, or if msb of a and b are negative but the msb of some, I mean the result is positive, then we get an overflow. So let's submit this. Okay, if you have a doubt regarding overflow, I'll explain that. Please let us know. Please let me know. Okay, and uh, feel free to uh, like, share, and subscribe. Like this video, share this video and this playlist with your friends, and subscribe to this channel. And if possible, please support my channel. Please contribute uh, to the UPI ID I'll mention below. So, and if you need any more kind of help from me, please let me know in the comments. If you want to talk to me one on one, if you want to talk to me personally, you can, you know, reach me out in my email address. So I'll share the email address as well below. Okay, in the description and in the comment section. So yeah, feel free. Okay. So yeah, it's a success. So let's move on to the next problem. So this is solved. So let's move on to this problem. 4-bit BCD adder. We have solved this previously. this kind of problem. Let me see what is there. We have a BCD thing. We solved something like this here in probably here. So 100-bit BCD adder, all these things we have done already. Okay. 1-bit adder named BCDF add that adds to this and carry in and produces sum and carry out. Okay. So let's do this. What we will do is, so there are 4 adders. Okay. Between 4 adders, so from 1 to 2 we need 1 wire. Between 2 and 3 we need 1 wire. Between 3 and 4 we need 1 wire. Between 0 and 1 we need 1 wire. So it's like between 4 adders we need 3 wires basically. Okay. We will write wire C, okay, internal, okay. And how many wires do we need? We need 2 down to 0. Okay. And we will just approach it in a normal way because there are only 4 adders. So what we will do is we will say if add BCDF add, okay, BCDF add BCD add 0. Okay. So it's like let's say BCDF add 0. Okay. And then what we give here is A, B, C and C out. So A, 3 down to 0, B, 3 down to 0, C in, C internal of 0. That is the output of the full adder. And then we have sum of 0, or let's say sum 3 down to 0 basically. Okay. So this is the structural way of solving problem. Okay. And then in place of C in, we will say C internal of 0. So that is the thing we now C internal of 0. Now that is what we will give as input to the next one. Okay. C internal of 0. In place of, it's like A 3 down to 0, B C in. First we give C in, then output is C internal of 0, C internal of 0, output is C internal of 1. Okay. And here we will say 7 down to 4, 7 down to 4, we will say 7 down to 4. Okay. And then we copy this and we say, okay, 11 down to 8. Okay. 11 down to 8. And then here we have 11 down to 8. And then here we have 11 down to 8. And here we will have C1. Here we will have C2. So we have used all of them now. And then we will just say, now we will have here 1, 2, 3. And here we will have 12. It's like 15 down to 12. 15 down to 12. 15 down to, so you can do this using genware also. You can do it in many ways. I'm just trying to do it in the simple way, just replicating things. Okay. Although it is not a viable solution when you are dealing with hundreds of full adders. Okay, so this is a short, simple way when you are dealing with only few of them, like 4, 5 max, or 10. Okay, not even 10, probably 4, 5, 6 max. Okay, A 3 down to 0, 3 down to 0, some 3 down to 0, 7 down to 4, 7 down to 4, 7 down to 4, 11 down to 8, 11 down to 8, 11 down to 8, A 15 down to 12, 15 down to 12. Okay, and then we have input as C in, C internal of 0, C internal of 0, C internal of 1, C internal of 1, C internal of 2, C internal of 2, C out. This is the C out we have. Okay, very simple, because this C in and C out we have to do outside the loop, or we have to do some assign statements. Okay, and for 2, 3 loop is not needed. I think I didn't do as, oh, it's not needed. It's actually structural, so assign is not needed. Yeah, status success, great. Good. We have our output matching with the reference output. Okay, great. So we can move on to the next problem, but this is where we stop today. Okay, so K-map we can do later. Okay, K-map is very easy actually. We will do later. Okay, K-map we will do later. So yeah. Okay. So before solving this walkthrough, uh, please do check these problems out yourselves. And then we have covered till this point. We have covered many things. So, getting started, and then Verilog basics, vectors, modules hierarchy, procedures, Verilog features, combinational, multiplexers, and arithmetic circuits. So we have covered all this. We came to Carnot map now. After that, we'll go to sequential. This is what we have covered till now. Feel free to practice the problems first. Try it out yourselves before watching at my solution. Okay. And if you have any doubt, please feel free to let me know. Please feel free to drop it in the comment section. If you have a different way of approaching this problem or any of these problems, feel free to drop that also in the comment section. Say which problem you have a better solution for, and write that down. Suggest, if you have some ideas or something. And please like this video. Okay, share this video, and share this playlist with your friends. And okay, and subscribe to this channel. Okay, please support this channel. Okay, if possible, please contribute. We will I'll share the details by which you can contribute to me, support me basically, so that I can give a bit more time and bring more contents like this. Because uh, like financial uh, support is of course needed, because I spend a lot of time and energy and on resources also, because buying a camera, buying a writing pad, so everything costs thousands of rupees. Okay, sometimes more than that, to bring you this kind of uh, material, this kind of videos. Okay, it costs my time, it costs my energy. So please feel free to support. uh, okay, anything helps. Okay, uh, because anything I get, I'll use to make the work faster and better, and give you better quality things. Okay, to give you back also, I need resources. Okay, because you obviously understand that. Okay, nothing comes for free. uh, Feel free to support, and if you want a one-on-one guidance, one-on-one consultation or something, if you want to connect with me, if you want to discuss something with me, okay, please feel free to reach out to me on my email ID. So Souvik, 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 GHOSH, 572 572 @gmail.com. SOUVIK, GHOSH, 572 572 @gmail.com. Okay. Thanks a lot for your support. Okay. We will solve the next set of problems from K-maps and all in the next video. Okay. So these videos will always be free for you, because I want to give you free knowledge. I want others to have access to free information, so that they can learn with ease when people don't have any means to support me. Okay, but when you have a good way to support me, you can support me. Otherwise, you can watch these videos for free and take benefit. Okay, and if this video helped you in any way, please do let me know. I'll feel very happy that okay, it helped someone. Okay, God bless you, and let's meet in the next video. Okay, till then, bye bye.